Good morning. So we are going to get into coding in a couple of minutes, but as I mentioned the other day, we do have an activity that we're going to do at the start of class, just to kind of get you thinking about stuff. So I had mentioned last week that this part of the course talking about algorithms and thinking about analyzing those algorithms, which we'll probably see on Monday. But at least understanding kind of common algorithms. We saw searching. We talked about linear search and binary search. And then now we're going to start talking about sorting. The goal of sorting is that I have elements, for instance, in a list, then I want to rearrange them so that they're in sorted order. For instance, now you may have discovered that in the list in Python, there's a sort method that will sort the elements in the list according to what Python thinks natural ordered order. For instance, if numbers, if you're sending, if you're strings, it'd be how strings get sorted. But the definition of sorted may depend on the type of element. So one day we talked about like a student record class, but we might want to sort the students by their name, by their age, by their major, and so on. So there's not one natural way of sorting them. So there are different algorithms for how elements go. I was a grad student a very long time ago. I had a job interview. And one of the questions was take image and write an algorithm for rotating the image. And a list of lists where each element is the color of the thing. And then I wrote what I thought was this very elegant thing. And then they said, no, can you do it in place? What they meant by in place is by not creating a new list, not creating a new image, the first one, but rather changing the elements in that list and moving the elements around without creating a new. So this is referred to as place. It means that you can move the things in the list. You can swap values of things in the list. You can shift things around, but we're not creating a new list and then putting the elements in. So to get you thinking about this a little bit, this is where I could use your help. We're going to do a little activity where you're getting 5 playing cards. And the idea is to think about a way that you could sort the playing cards in descending order. Whether ace is high or low is up to you to decide. But think of the cards as being a list. And so it's not so much like creating a new list, but keep them 1, 2, 3, 4, 5. And then how do you move them around? Sort them. So we'll do this, well, kind of in pairs. Somebody will show up. If it's already sorted, like coincidentally, when you get them, just mix them up. So think about how would you sort them, but you can't like pull the smallest one, then pull the next smallest one, because that's creating a new list. So how would you move them around? Like think of how would what's the approach for moving them around in the list so that they end up being sorted. How could you There's no right answer.
That's
Or you can talk about classes that you want to take next fall, but you can't just sit there in awkward silence.
like regular fun. Right, that in local philosophy, my writing I'll see one and two.
Oh, true.
Yeah. It's like one day so far. Yeah.
I should have seen that one and like it was like a. I mean,
Yeah.
about like.
Just the Policy one, but yeah, he's good. Yeah.
Okay, we'll move on in a minute and then start talking about one way that you could approach this.
I did not.
So there are a variety of ways that you can do this, and talk about two common ways that are done, at least in computer science. And so if you came up with something that works, that's great. If you didn't, that's okay too. Before we proceed, I am going to put this out there. I think that the next 4 or 5 lectures are the hardest conceptually in this class. I think like this week and next week are the hardest conceptually. And I say that it's past the withdraw date, so you're stuck with me. But I say that just so you realize, like, if you're not getting it the first time, that's okay. It's okay to ask questions. It's okay to go to office hours. I have hardly anybody ever come to my office hours. It's so sad that no one comes to my office hours Thursday afternoons, 30 to 3, I think. So if you are like, oh, I don't really understand the things we're talking about, it's okay to come and ask questions. It's okay to ask questions in class. It's okay to ask the ninjas. Okay, it's not really okay to ask ChatGPT to explain stuff to you, and I love that. But it's okay to like look at the resources that are approved. You struggle through it. You learn by overcoming struggle. So I'm just going to put it out there that I find historically these are the toughest things to understand. But you will get there. You will get there. But it's okay to ask questions. It's okay to not understand it at first. So I'm going to talk. Whoa, that's not. Sounds like the class is over, but it's not. Wrong slides. I'm going to talk about one possible way of sorting them. And there's a lot of animations and stuff in here, so take notes if you feel compelled to do so, but I will send you the slides after class today. So one possible sorting approach is to go through the list, of elements from left to right. And if a value is greater than the one that comes after it, then swap them. And we'll see an example of this in a second. The idea being that I want the larger values to be on the right or the end. And so what I'll do is I'll go through the list. Again, I'll do an example in a minute. Go through the list, and then if a value greater than the one that comes after it, then I'll swap them and just change their positions. after I go through the list, the largest value will be all the way at the end. So if I start with my list and I go through it once, and each element in the list, if it's larger than the one next to it, and again, we'll see this in a second with an example, larger than the one that comes after it, then I'll swap them, and that way the largest one is moving all the way right. Then I do this again, starting at the beginning, and if it's something is larger than the one that follows it, I'll swap them. And then now what happens is that the second largest value will be in the right place, because it wouldn't swap with the last one, which is the largest one. Again, we'll see this in a second. And we would continue doing this and so on until the list gets sorted. So I'll leave this on the screen for a second here, but I am gonna walk you through an example of this using 5 letters. But the idea is we go through the list and we just swap something with anything that's bigger than it. If it is, sorry, we swap it if it is bigger than the thing separate, so the bigger things are moving. Right. So let's see an example of how we would do this. So let's say this is our list, and we'll say this is the original order of the list, and we're going to go through this list once, and if starting with the D, that's at the beginning. And if it's greater than the thing that follows it, then we'll swap them. So D, what follows the D is B. D is greater than B. Like D comes after B in the dictionary, so it's greater. And so we're going to swap them. So now we have this. So to go back a slide. So we just swapped D and the D so that the D goes moving to the right. Now we do this for the next element, which happens to be the same element, but going through this left to right, one element at a time, it happens to be the same element as the first one because we just swapped them. But we take that element, we look at the one that follows it. Do we swap? No. It's a trick question. It's not a trick question, but no, we don't swap them because D is less than. And if you think about it, we want the E to be all the way at the end. You know, and I know that E is the largest value, so we want the E to be all the way at the end. So we wouldn't swap the D and the E. So now we go to element 3, which is the E. We look at the one that follows it. Do we swap them? Now, yes, because E is greater than A. Comes after A. So we swap them. Now we move to element 4, which happens to still be the E. We look at the one that follows it. Do we swap them? Yes, because E is greater than C. We don't need to consider the E and what follows it, because there is nothing that follows it. We're at the end of the list. And so what, I already said this, but what have we done? What is the result? The result is that the largest value has bubbled way all the way to the right. By starting at the beginning and swapping larger values with smaller values, the largest value has bubbled its way all the way. So this code, which I'm going to write on the board also, is what I'm calling this bubbling of in this case, the largest value moving from left to right. So why is it for I in range len list -1? Well, remember that we started with like first element, second element, we started first to the second, second to the third, third to the fourth, fourth to the fifth. But we didn't compare the fifth element to the sixth element because there is no sixth. We didn't compare the last one and that follows it because there is nothing that follows it. So only, in this case where the list is 5 elements, we only did 4 comparisons. First to second, second to third, third to fourth, fourth to fifth. So that's why it's -. Then we said if an element greater than the one follows it. The list of I. If this of I, that's the element we're looking at, larger than the one that follows it, then we'll swap them. And we'll have to implement this swap function. We'll assume that it swaps the elements at index I and I plus 1. We'll assume that it swaps the value with the follows it. So this is what I'm referring to as, you know, the bubble function, that it's moving the largest element all the way to the right. What questions do you have? Ask questions. Great question. So does swap need to be its own function, or is it just 2 lines of code? It turns out it's going to be 3 lines of code. I know. Now it's like, well, then I take back my question. Yeah, I'm going to treat it as a function, just to talk about later on as an example of a function. But it is just a couple lines of code. We are not done with this example. You might be like, whoa, wait a minute, the rest of it is not sorted. Yes, I know. All we've done is moved the largest element all the way to. But we're not done because the rest of it is not sorted. So we're gonna do this again. We're gonna go through, start at the beginning, go through this again. The idea being that larger values be bubbling. So this is the same list as it was before. The E is in green because it's in the right place already. And we're going to go through this list again. So we start at element number 1. So now we're bubbling again. So what I'm showing you on the screen is the same as what's on the board. So we're doing this again. We start for I in range 1. So we start with I in 0. We say if list of 0 is greater than list of 1. We compare the B to the D. B is not greater than, oops, that should be less than D. B is less than D. D is less than D, so don't swap them. Now I is 1. So we're doing this on the board here, this bubbling. We're doing it again. Now I is 1, so we look at element list of 1, B is greater than list of 2, which is A. Yes. So then we do swap them. That's this code here. So we swap element 1 with element 2. Now I is 2. List of 2 is still D because we just moved it to the right. We look at list of 2 compared to list of 3. D is greater than C, so we swap them. Now we're done, but we can keep comparing. But it's not in the animation, but we could compare D to E, but not greater than D. D is already in the right place. But now what's happened is that when we bubbled again, the D ended up in the right. So that's why I have it in green, because now the D is in the right place. Yeah, so the question is, if I wanted to sort like in descending order, I guess you would just switch the if statement so that smaller. I have to go backwards. Oh, no. Okay. The smaller ones would bubble to the right. So what's on the board here, this bubble, that was just to move, for instance, the E to the right place, second time, the D to the right place. But I don't want to do the bubbling once. I need to do it as many times as there are elements. So outside of here, I'm going to have another for loop. We're going to call it J, after I. For J in range length of list minus 1. Now you might say, why, again, is it length of list minus 1? I don't have it in the animation, but the C is already in the right place. When the B moves to the right place, the last element, the A, must be in the right place, because everything else is in the right place. So I don't have to do this 5 times. I really only need to do it 4 times. I need to move the E, D, the C, and the B. And then I know I'm done because there's only one left, and it must be the smallest one. So now it's like a slight efficiency improvement. This minus 1 here. This minus 1 inner loop. Have to have that because we don't want to compare the last element to something that comes after, because I don't know that we've seen a for loop within a for loop in this class. I was trying to think of another example, maybe in some lab early on. But for this classic example of the loop with loop, notice in the inner loop, what I'm calling the bubble, we're not using J. The outer loop just controls how many times we do it. The inner loop, moving it. So this algorithm, as it says on the screen, is called bubble sort. Bubble sorts is classic computer science algorithm. Is not a particularly good algorithm. You may be thinking like, well, it feels like a lot of work, things right, and so on, and you write about that. But it is a good place to start when thinking about sorting. It is a good place to start when thinking about for loops and loops within a loop. And momentarily, it's also a good place to start when thinking about swapping out. So what's on the screen and what's on the board are hopefully the same thing. Yeah. And this algorithm is called bubble sorts. We're going to implement this in a minute. But I think that the big takeaway from bubble sort is like this inner loop, what it says on the screen and on the board is the bubble moves one element into place. But I don't want to just move one element into place. I want to move all of them into place. That's why I have to do this in an outer loop. So I do this multiple times. What questions do you have about bubble sort? So now we're going to go into code. So we'll run update 21. Yes, 1. And so in week 10, directory did the code that I wrote in class on Monday. So that's in your sorting directory. If you're starting the lab today, you might want to use that in objects list Monday. But say we're going to use the sorting program. So there's a lot of code that's already provided, and I'm going to walk you through it, but everybody's with me. There is a lot of code in this program already, and there's one part that's a little bit hard to keep track of, maybe. So the main function is here on line 7, and it's just a whole bunch of examples where it has a list. It prints out the list before sorting it. It calls this function do sort, which sorts it, and then prints it after sorting. And then there's this other function is sorted that tells us if it's sorted, and it repeats this a bunch of times with a bunch of different lists. Later, there's this code on line 36 that compares the execution time of different sorting algorithms. We'll deal with that probably Monday. To help us change between different sorting algorithms, there is this function do sort, which all do sort does on line 38 is call another sorting function. And that just allows us to easily change how we do the sorting function. So you can see on line 48 called bubble sort, which we're going to implement in a second, which is also on the board right here. And then on line 51 is the starting point of our swap function, which we use in bubble sort, which we're going to come back to in a couple of minutes. On line 68 is the header for the bubble sort function, and we are going to implement this now. So if you're with me, we should be on what's left on line 78 on this, and we're going to implement the bubble sort function here. So the argument to the bubble sort function is the list that we want to sort, and this function doesn't return anything. Rather, it changes the list as a side effect. We're on line 71. As a side effect, it changes the list, and it does this in place. And all I'm going to do is just type what's on this board. Just put it out here because this is the bubble sort algorithm. So we have this outer loop. We have this outer loop which repeats so what's on the top line of the board and what's on line 78 is this loop that allows us to do this number of times, repeating the bubbling, or the bubbling moving one element all the way into right as far as we can go. Then what I wrote on the board, what was on the Google Slides a minute ago, is bubbling. That's this loop, regular for loop, for here, where it's bubbling one element as far to the right as it can go. The bubbling is comparing each element to the one that follows it, the one to its right in the list. So if list of I is greater than list plus 1, the element greater than the one that follows it, like in the B, yes, then we do swap their positions, and that'll be this function here. We haven't implemented the swap function yet. And another thing I thought of is, even though it is only 3 lines of code, we are going to use this swap function in a different sorting algorithm, so that's why it's this function. So I think the kind of common misunderstanding of bubble sort is just thinking that it's just this inner part. That's only moving, that's going through the list once, and it's moving the largest thing to the right, moving that element as far to the right as it can go. But we need to do this multiple times so that all of the elements end up in place. What questions do you have about that? So let's talk about this swap function, which is up here on line 51. I am going to erase what's on the board. It's also in the code, it's in the slides, so on. So the swap function takes the name of the list that contains these values and the 2 positions that are I and j. Now, in the bubble sort function, I was using j to control the outer loop, I to control the inner loop. and those are not necessarily, those values are not necessarily I, J here. So to clarify that, I'm going to change this to A and B, just so it's not, doesn't feel like we're using the same variables. So this swap function is going to swap this of A with B. In that bubble sort, the values are like I and I plus 1, which I traced. But I want you to, I don't want you to think it's the same I and J at all. It's just, I have a list, and I've got two values, two indices, and so another way I can say it here is swap list bracket A with list bracket B. And I hope that helps you think of this outside of bubble sort, regardless of how I and J are used, because we are going to see it in another example a little bit later. If I have x equals 5 and y equals 9, sidebar, if I have x equals 5 and y equals 9, how do I swap their values? It's tempting to say x equals y equals x. Does that work? If it did, would I be making a production of it? No. What happens when I say x equals y? That now x is 9, but what is y? Still 9. So now x and y are both 9, and so all I'm doing is setting y equal plus to the 5. So I can't simply swap values with 2 lines of code. I need a temporary variable. We'll say something like temp equals x. So this on the board here does not work. But I can have a temporary variable that temporarily holds x. Now I can say x equals, now I can say x equals y. So I take the 9, put it to the x, but I haven't lost the 5. I can say y equals 10. So to swap the value of 2 variables, I do need a third variable to, well, it's a math trick. But regardless, I do need this third variable. Temporarily hold it while I swap them. And the same is true even if these are list elements. So I can't simply say list of A equals list of B, then list of B equals list of A. That would be this mistake that I make here. Rather, I could say temp equals list of A. Now I can say list of A equals list of B. But I have not lost the original value of list of A. Same way here, I did not lose the original value of x because I temporarily put it in this temp variable, which I would call TMP. So now I can say list of B equals temp. So the swap function, the swap function is going to change. It's not going to return anything, but rather it's going to change the elements in the list using that third temporary variable. So in this example, we've implemented bubble sorts, which has the loop within the loop, and then we need, for a bubble sort, we need to swap the values as part of the algorithm. And then I'm going to run it in a second to show that it works and just show what the output of the program is. But what questions do you have about bubble sort or swapping values? for anything else we've talked about. So in that case, if I do, so again, if you look at the main function, it's just creating a list, printing it out before it sorts. It calls do sort, and then do sort calls bubble sort. So do sort is just kind of a placeholder, so I don't have to like keep changing all of these lines of code. And it's going to do this for a bunch of lists, some of which are already sorted, in fact. So the program is testing our sorting function. It's printing out what's before sorting, after sorting, and then there is this other function called isSorted in their code somewhere, and it's telling us sorted or not. So in the last like 10 or so minutes, I'm going to move on to another sorting algorithm. And it's similar, I suppose, to bubble sort in that it's going through the list multiple times and looking for particular elements and swapping things around. And then we'll talk about probably on Monday about the efficiency of these algorithms. So I'm going to go back to the slides for this part. Okay. So another approach to sorting, you might say, well, if there's better approaches, why did you teach us the bad one? Right? And again, I taught you the bad one. It's not bad. I measure badness. But again, I want to talk about the loop within the loop. I want to talk about the swapping function. But here's, and you are going to have to implement it in Lab 9 next week. So there's practical reason for this. But another sorting algorithm you're going to need to implement in Lab 9, which is next week's lab. It's this one, which we'll use to take us to the end of today's lecture. So in this other sorting approach, we look for the smallest value, and then in the list, and we swap it with whatever is in the first element. So rather than compare, and having those values bubble to the right, or whichever direction we go, we'll just look for the smallest value and then swap it with whatever happens to be in the first position. And again, I'll walk us through an example of this in a minute. Then we go through the list again, and we look for the next smallest value. We swap it with whatever happens to be 1, which is the second element. So now the first 2 elements are sorted, and then we find the next smallest value. We swap it with whatever is in position 2. That'll be the third smallest value. And so we keep doing this, always looking for the smallest value and swapping it with whatever happens to be in the right position, so that we don't have to do so many comparisons and have the thing, keep comparing and bubbling, but rather just look for the smallest thing and then put it in the right position. So I'm going to walk through this example. I guess I'm going to walk through it twice. I don't remember now. Oh, yeah. I'm going to walk through it twice, once without the indices and once with the indices. That'll bring us to the end of lecture, and then on Friday we'll pick this up and talk about the implementation. So here, let's say this is the list. We want to sort it. We look for the smallest value. The smallest value is, no one wants to say it because no one ever wants to answer a question that's so easy. It's like too much risk. The smallest value is A. So the smallest value is A, which we know because maybe we searched, not searched, but we looked through the whole thing for the smallest value. And then where do we want the A? We want the A in the first position, so we just swap the A and whatever happens to be in the first. So we found the smallest value. And we know where we want it to go. I'm not going to deal with like swapping and comparing and swapping. I'm just going to to compare because I need to find the smallest value, but I'm just going to swap once. And so then I move the A where it needs to go, and now A is in the right place. And I suppose you could look for the largest value and put it at the end. Same thing. But it's not like bubble sort, because bubble sort, remember, was like compare and swap, compare and swap, compare and swap, compare and swap. This approach, just we have to compare because we have to look for the smallest one. We're only swapping once. We swapped, in this case, the D with the A. But we're not done yet, so we're going to look for the next smallest value, which is the B. We want the B to be right after the A, so we're going to swap the B and whatever happens to be there. So again, to go back, we found the next smallest value, which was B. We know where we want it to go. That happens to be where the E was, so we swapped the B and the E, and now the B is in the right place. Now we look for the next smallest value. This is C. We know where we want the C to go. We want the C to go after the B. The D happens to be there, so we're going to swap those. We look for the next smallest value. That's D. We know where we want it to go, which is right after the C. That's where the E is. So we swap them. And now, for the same reason as before, we don't have to look for the smallest element in the list of left, because it's got to be only one left. Now the list is sorted. Right. So, so this approach is similar in that we're still swapping things, but rather than kind of having something bubble and move, looking for the smallest one and then swapping it. So I'm going to walk through this one more time with the indices, and as I do that, I'm going to write it on the board. So let's see. I need some way of finding the smallest, it's not finding the smallest value, but finding the index of the smallest value. So this finds index of smallest value in the list, starting at index I. And that is, I think, the trick. Is that I'm going to have this function called find smallest that finds the smallest element, sorry, finds the index of the smallest element, smallest value, starting at index I. Index of smallest value. Starting at index I. So as it said on the screen, find the smallest value between indices 0 and 4. So the first time this I is 0, we want to look for the smallest element in the whole list. We want to swap it with what's at index 0. So I'll put that into a variable called SI. SI is going to be the index of the smallest value. So in this case, the index of the smallest value is 2. If you look at the original, the index of the smallest value is 2. Just at the top. Or if I go back, the index of the smallest value is A, its index is 2. So the index of the smallest value 2, so SI, smallest index, 2, then I'm going to swap it with element 0. Well, this. I, which is first, starts at 0, so initially I is 0. Actually, let me write it this way. first I find the smallest index, starting at index 0. Hold this. Then I swap to that 2. Then I swap what's at element 0 with what element 2. So now the A is in the right place. The second time I do this, and I find the smallest in the list, where do I start looking from? From 1. So if you're like, yeah, right, I see that now, because A is still the smallest in the list. I already know that. I know that's in the right place. But now I'm going to look for the smallest starting at index 1. When I find, so the smallest starting at index 1 is B. B's index is 3, so this SI is 3. Swap element 3 with element 1. Because I want the B to be in that place. I'll do one more. There we go. So now, no loops on the board, right? I'm just going to write a loop and then I back off. But the first time I find the smallest index of the smallest element starting at 0, and I swap it with element 0. Then I find the smallest starting with element 1, because I know that element 0 is already in the right place. So I don't need to look for the smallest one. So then I find the smallest one starting at element 1. I swap it with element 1. Now I do the same again. For element 2. Because I know the A and B are in the right place, and those are the smallest. So if I find the smallest in the list, it's going to be A again. I don't want A. I want the smallest in the gray part. I want the smallest in the unsorted. I want the smallest starting at index 2, because at this point I know index 0 and 1 are sorted. The smallest is C. C is index 4. So SI will be 4. Where do I want the C? I want it at element 2. Because that's the third smallest element. And then one more time, and then it's done. So this algorithm is called selection sort. And selection sort is its middle part here, which is on the board, finding the smallest index, swapping it. But you'll notice, and this is where I was started with, that each of these pairs, this number is increasing. And so we can do this in a loop, and then that's the point of the outer loop. So I'm going to stop here. I told you 25 minutes ago that this is partly the hardest part of the class. It gets worse. But if you're like, no, not ready for that right now, that's fine. We're going to come back to it on Friday and talk more about selection sort then. But you know, if you have some spare cycles to think about. Yeah, so the question is, do we need to check if the list is sorted after every swap? I think no, because
It needs to like randomly assign.
yeah, it's probably more in general. I think we wouldn't want to keep checking
Once we're in the dark,
because
they don't
costs as much to check if it's sorted as it does.
I got
it just randomly tries.
All right, see you.
But so it could also try the same. Well, it's just swapping two values. So we're gonna see when it gets to 50 million, we'll give it sense.